Hello all. In this video, I'm going to give you a super short introduction to what machine learning is all about. We've already used machine learning models, but now we're actually going to take a look at what they do. And I'm also going to focus specifically on machine learning models, deep learning models that we use for computer vision. And image classification is the main one we're going to focus on because it's the most straightforward of any of them. So I will see how many videos this ends up being, but for right now I'm going to try to cover both of those topics in this one video. All right, so the first question you ought to have is, what the heck is machine learning and how does it work? This is a key idea for understanding anything that's happening with artificial intelligence right now. We're not going to talk about all of the different kinds of machine learning that are out there. There are too many. We're going to focus really on just a few. So what is machine learning? Machine learning is an algorithm that finds patterns in data. This is absolutely the core of what machine learning is all about. We collect up some data, we hand it off to a machine learning algorithm, and it looks for statistical patterns, usually driven by some task, although there are approaches to machine learning that don't involve a task. But a typical task might be that we have a data set containing a bunch of examples of something. So for instance, if we're talking about computer vision, we have a bunch of examples of pictures of different kinds of animals, and we'd like to build a program that categorizes those animals. So we give the data set to the machine learning algorithm, and we ask it to predict the category. What kind of animal is this picture? When we actually train the model, when we actually run the algorithm that looks for those patterns, we have to tell it the correct answer in this case. We have to tell it, this is a dog, this is a cat, this is a horse, this is a pig. And then we hope that it will find patterns in the data that will allow it later on to make those determinations correctly on new images that it's never seen before. And that's another key about machine learning. The goal is not to memorize a set of data and just be able to spit that data back out exactly as it was. We can do that, but that's not really machine learning. What we want is to train the data on some set of examples and then have it be able to work on new examples it's never seen before. So in the case of something like a large language model, it's trained on billions of pieces of text of various different kinds, blog posts and novels and Twitter conversations and all of those things. And then our goal is that you can type things into it and it will respond correctly, adequately to what you have entered. I'm going to show you, this is a XKCD, which is a great sort of techie oriented comic. And this is one of his comics about machine learning. And so what I want you to note here, and looking at the picture, we've got a funnel labeled data, and we've got some matrices in here and some math symbols, and then we have answers coming out of a box on the other side. And it says, this is your machine learning system. Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. And what if the answers are wrong? You just stir the pile until they start looking right. This is particularly funny to those of us who work in AI because this is not an inaccurate description of machine learning. It's a little bit tongue-in-cheek, but fundamentally, machine learning systems use a whole lot of linear algebra, matrix operations, sort of like the ones that we've already worked with images, and they mush the data around to try to produce the answers that we've told it we want. Okay. Why would we use machine learning? Well, I'm in AI. Some people in AI are driven to understand human and animal learning, and we use machine learning as a vehicle for doing that. That's not the primary use of machine learning, but it is one. It's just like, what does it mean for a system, for an entity to learn something And what would it mean if we could do that in a computer? How might a computer learn? We can also be focused on wanting systems that can adapt to changes in their environment. If we just define rules for how something should behave, if it sees a situation it's never seen before, it may not respond appropriately. So maybe what we want is to build a system that can dynamically deal with new situations. But the main reason that we use machine learning is because we don't know how to solve the problem otherwise. You all have played around with computer vision algorithms like the background subtraction or the motion detection or the trying to find a ball by using thresholding and color tracking and making masks and using fine contours. We've done all of those things and they kind of work. But when people in computer vision wanted to do more complex tasks like detecting faces in images, what they found was they just didn't know how to do it. They couldn't come up with the right rules to make it work. And so they went and used machine learning and have had tremendous success with that. Similar things have happened in the realm of like natural language processing, the things that the realm that large language models come from. So the computer is better at finding statistical patterns in large, complex data than we are. It doesn't get daunted by the fact that there are 300 different numbers and they somehow mean something. It just looks for patterns in data. That's what it does. I have a bunch of terminology here. I'm not actually going to go through all of it. It's not super important for us. I'll just note that we are going to focus on the classification task for the most part. We'll look a little bit at some other computer vision tasks, and we're going to focus on training from scratch. So don't worry about these too much. All right, so then there are different categories of machine learning out there. I've listed a bunch of them here. We're going to focus on supervised learning, but you can take the statistical machine learning class, Stat 253, or you can go and take my Intro to AI course later, and we talk more about these other kinds as well. All right, so supervised learning is the most common type of machine learning. This is where we have input examples, like those pictures of animals, and we have labeled each one with the correct answer. And we feed those two things to our machine learning algorithm, and it looks for features in the pictures that allow it to correctly identify what category something belongs to. This is probably, I would say, 75% of what happens in machine learning is supervised learning. Self-supervised learning is sort of a special case of this, and large language models fall into this self-supervised learning plus additional. They've augmented them with additional kinds of learning as well. Self-supervised learning to me is still supervised learning because we have a correct answer. It's just that the target values are somehow an intrinsic part of the data itself, so we don't have to hand label the data. It's just there for us. So the canonical example are large language models. You train a large language model by giving it a sequence of words from a text and asking it to predict the next word. Or maybe sometimes you give it a sequence of words where one has been left blank and you ask it to predict the blank word. So it's given, we have the text. We know what that blank word was. We know what the next word is supposed to be. So we can correct the model by telling it, no, the correct word was actually X. It's just that we humans didn't have to go and do that. It's an automatic process because of the nature of the data. All right, so that's self-supervised learning. There is another kind of, and the example I gave was sequential data. There is another kind of self-supervised learning where we train a model to replicate itself. Talk to me offline about why we would want to do that. Two other kinds of learning. There's reinforcement learning. This is kind of one of my favorites, although I don't do it in my own research. With reinforcement learning, we don't give it the correct answers. But we also don't give it no guidance whatsoever. So usually this happens with an AI system that is online performing a task, and it gets feedback from its environment about whether it's being successful or not. So it gets rewards or punishment based on the actions that it takes and how those play out in the world. So for instance, if I wanted to train an AI system to play Mario Kart. I would set it down in the world, and I would reward it for trying anything, like getting the car to move. But then I could also reward or punish it based on how well it stays on the track, whether it's pointing the right direction, all of those kinds of things, without actually telling it exactly what move to make in every scenario. So reinforcement learning is a lot of fun, and a lot of AI interest has gone into that. Large language models have incorporated a kind of reinforcement learning as well as a later stage in their processing. Unsupervised learning, this is really interesting to statisticians, and it is useful in other places as well. It's kind of a data sciencey thing. You give a system input examples, but you don't tell it anything about correct answers. You just say, find some patterns. And maybe what it's trying to do is to cluster things by similarity, or there are other approaches as well. This is an interesting approach because we aren't telling it what it should be finding. We're just saying, what are the patterns here? This is used a lot for data mining, which is a sort of a data sciencey thing that people do, just to just look for patterns in data. The classic example of this once was, and this may be apocryphal, not a real example, but the example came up that a grocery store chain was doing some data mining on purchases that customers made, and they discovered that there was a strong correlation between people buying diapers and beer. And so they reorganized the store so that the diapers were on one side of an aisle and the beer was on the other side of the aisle in order to increase sales. That's the story. All right, so there are also some systems that are semi-supervised, where we have some data that has been given the correct answers and we have a larger set of data that is not. And so it tries to use the small set that it has and extend it to cover the unsupervised ones. So there's a lot of work on violating these rigid boundaries, but these are generally the types of machine learning that are out there. Like I said, we are going to focus on supervised learning, like almost everyone else. So let's take a closer look at supervised learning. There are some notations here that might come up in other contexts. So we have a training set, a set of examples, and the correct outputs for those examples. And we want to send those to an algorithm that's going to learn from them. So when we talk about the training set, it is often described as X and Y put together. We're not talking about Cartesian coordinates here. We're not talking about pixel locations or anything like that. X is a vector. It's like a list, an array of a whole bunch of data. And Y is also a vector that has the correct outputs. And these x1, x2 through xn, those could be vectors themselves. Those could so x could be a big matrix, multidimensional maybe even, and y is really usually just a vector of results, of correct answers. So we have this training set. Again, we build a model. The algorithm constructs this thing that captures the patterns that it's finding. And we call that thing, that artifact that gets created, a model. What the model looks like varies depending on what machine learning algorithm you're going to look at. We are going to look at convolutional neural networks. That's just like the most basic thing you do in computer vision with deep learning. But fundamentally, the algorithm takes in the data and the patterns are embedded in this thing that we call a model, that we can then pull out of that context, and we can use that model other places to perform a task. Again, the goal is generalization. It is easy to build something that can memorize a data set. It's hard to build something that generalizes appropriately. There are two terms that you should know about when we train these models. So when we run this algorithm and it builds the model, it might not work very well. And there are two scenarios where we need to tweak the model and try again. I'm going to start actually with the bottom one. Underfitting is when the model doesn't learn very well. It just doesn't succeed on the training data. That's unfortunate, but it means you need to try again. You need to try building a different algorithm, try using a slightly different form for the model, various things that you might need to do to get it to the point where it can learn the training data. Overfitting is also a problem because this has to do with generalization. A model is overfitting if it learns the training data really, really well, but it doesn't generalize well to other examples. It's called overfitting because what's happened is it's noticed patterns in the training data that don't correlate to the actual real world problem. They're just specifically in this data. And it uses those patterns in order to solve the problem, but then that doesn't work in the real world because they're just peculiarities of the data. So I can give you two examples of this. Someone created a machine learning model to tell the difference between dogs and wolves, particularly I think like huskies or malamutes, the kind of dogs that look a little wolfish versus pictures of actual wolves. The model was extremely successful on the training data, but when they tried it on other data, it failed miserably. And when they looked at it, they realized that in their training data, all of the wolves had pictures taken of them in the wintertime, and there was snow in the background. And all of the pictures of the dogs had been taken with green grass. The model had noticed the difference between snow and green grass and just learned that instead. So it was doing really well on the training data, and it really wasn't going to do very well generalizing to outside of that. There's another example from the medical field where they were training data on to distinguish between, say, the presence of a problematic, say, mole on a body versus one that was harmless. What they failed to recognize was that many of the images of the harmful moles had a ruler on the image that was just automatically placed there by the machine that took the image so that you could get the scale of things. And they didn't have that for the ones that were not harmful. And so the system had simply learned that that feature was important and was learning the wrong thing. So we have to be really careful about this. It means that what we end up doing is setting aside some of our data and not letting the model see it so that we can then use that data to test its performance. And we want to ultimately test it on other data that we didn't even have in our hands at the time that we trained it. Because if it's overfitting, we get really bad results. All right, so here is what happens. So suppose that you want to actually do this. What would it look like? The first thing you would have to do is to find a data set. Say here, build a data set. It depends on how much time you have. Building data sets can take weeks, months of time. For a really large deep learning data set, they are hiring people to do this work because it takes, a year of work hours to actually create the data, and so they can't do it that fast. But otherwise, you might be able to build a data set, or you can find an existing one. The biggest task is actually this, labeling each example with the correct answer. That takes a lot of time. Then you need to do some pre-processing on the data, and this varies depending on what algorithm you're going to use. That could be just transforming the data. So with our images, for instance, we're often going to change the scaling. Our scaling has always been between 0 to 255 for color pictures, right? We're going to rescale them so that they range between 0 and 1 because that just makes our machine learning models happier. But there are also things you could do, which you can learn about in other courses. Principal components analysis lets you figure out which parts of the data you have are most important, and it eliminates the rest. And then we divide up our data, as I said before, into training data and validation data. The training data is what actually gets input to the algorithm. It's what the algorithm sees. The validation data is a random selection of examples from your original data set that you hold back. And we use it to check to see if the model's generalizing correctly. So the typical process is you run the algorithm, it gives you a result on the training data, it tells you how well the validation data works, and then if it's not working, you go back to the model, you change the algorithm, you change the model, you run it again. And you keep iterating that process until you get the performance that you like without overfitting or underfitting. You also have this third kind of data that you can create, like the best quality work is going to do this. When we're working on these things in class, we can leave it out. Testing data. This is data that you never use any point in the process. So it's a smaller random set of the data that you had initially that you hold back in a vault somewhere. And when you're all done and you think you have the perfect model, you run it on that testing data and see how it does. Because in that iterative process where you're looking at the training data and the validation data and you're tweaking the model, you could very well be introducing some bias of your own that causes it to only work well on the training and the validation data and not on other things. The other thing you could do with testing data is go out and collect additional data from a different source, ideally, and then see how your system operates on that data. All right, so this is our overall process. I'm going to talk a little bit about evaluating models, and then I'm going to pause, and in the next video we'll talk about convolutional neural networks. All right, so when we evaluate these models, there's a couple of terms that you should know. There are lots of additional terms if you really wanted to dig into this. Loss is the big one that you'll see, and it isn't a word that might make sense to you. Loss here is basically a synonym for error, incorrectness. So when we're actually running these particular models, we will present, say, an image, and we want it to categorize it as what kind of animal it is. The image goes through the model produces its prediction. We can compare the predicted value to the actual value, the predicted value to what the correct answer is. And loss is the difference between them. How wrong was it? How right was it, but how wrong was it? The larger the loss, the worse the model is doing. As we train these deep learning models, loss will decrease. It will get more and more close to giving the correct answer. So there are lots of functions and formulas for calculating loss. We're not going to worry about learning those right now, but just know that that's a thing, that you could choose a different way of calculating what the error means. And we talk about that in other places. There's another measure that we use, which is more of a positive one, and that's accuracy. So when I run through a set of data, accuracy is what percentage of the time it gave the correct answer. Sometimes we have to interpret its answer to decide that it's being correct, but fundamentally it's just how often did it give the right answer versus the wrong answer. If that seems like it's the same as loss, there's some subtleties here. Like loss is looking at the actual numerical output that the model produces, and it's looking at a numerical sense of what the output was supposed to be, and it's actually arithmetically calculating the difference between them. Accuracy is reinterpreting the model's output to be an answer, and then figuring out whether it's the same as what the correct answer is. So it's at a slightly different level in terms of what we're getting from it. All right. So this is not intended to be a thorough introduction to machine learning. We're just playing around with it in the context of computer vision to see what it can do. And so I want you to understand the gist of it, and then maybe you go on and you take one of these other classes that we offer and you learn a lot more about it. There are also some really great online courses as well if you want to dive into this stuff. So don't feel like you have to memorize all these terms. Just know that there's this whole structure behind it, and if you understand the general process, then the details will take care of themselves. All right, I will see you very soon.